You see, in our last class, we discussed about nuclear models in general, right? What happens in the atomic nucleus, how to try to understand, how we should proceed to understand this many body quantum system. And then we talked about the shell model. Thereafter, you see, we just wrote down the many body quantum system. We tried to understand it using the Hamiltonian formalism. Basically, we wrote down the Hamiltonian, and then we have the kinetic term, a potential term, and then you see in the potential term we just considered the two body interactions only. After that, we added and subtracted one body kinetic terms, and then we assumed that if it would be so that the residual term, which is two body minus one body, it vanishes, then we have a complete mean field. That means a single nucleon moves in the field due to the created as a result of all the other nucleons. And also it is interesting to know that there is no collisions because it is forbidden by the Pauli's exclusion principle. Now we discussed all these things, and after that we talked about regarding what should we choose as a potential UR, right? So we were talking about the choice of this potential, and the first choice that we did was harmonic oscillator. Now there are two particular reasons. One is the solutions of harmonic oscillator, they are very well known, right? And another is that when we do a Taylor series expansion, then near a maxima or minima the linear term is 0, then we have a constant term, and so the next leading term, which is non-zero, is quadratic in nature. So basically you can say very close to the minimum or maximum or extremum, basically the nature is somewhat very much closely described by the harmonic oscillator type potential. Okay, so with this in mind, you must remember that we did a rigorous estimation. You might be wondering why we are doing so much about so much mathematics we are doing. We introduced the Lagrange polynomial normalizations and all that. You must remember that. And at the very end, you will also remember that we obtained these results. You see, we obtained this result. E by h cross omega is of the order of half delta 0 plus 2 to the power 4 minus 1 by 3 delta 0 plus 2 to the power cube, and so on and so forth. And after eliminating this lambda 0 plus 2 from the above equations and keeping terms of larger order in delta 0 plus lambda 0 plus 2, then finally you see we will get this relation. E by h cross omega is approximately half into 3 by 2 a to the power 4 by 3. And so this just means that h cross omega, so basically we get some idea about the harmonic oscillator frequency estimation. So this is the result that we wanted to prove in the last class. Okay, I remember I told you to do this yourself and find the values. Maybe you have done, and you can check these values yourself. So this is minus 1 by 3 and this is 4 by 3. Okay, now the giant dipole resonances, do you remember what they are? So basically giant dipole resonances, they correspond to excitations where delta L is equal to plus minus 1. That means we have got different shells in a harmonic oscillator. It means not this one, excitation between not this one, but it is between these two or maybe these two and something like that. They correspond to the giant dipole resonances. Okay, and the position of the peak varies with the mass of the nucleus as given by this here. And so this is a good example of the application. See, this giant dipole resonance, there the position of the peak basically varies with this mass as this term. Okay, so this equation basically gets a sort of experimental verification in giant dipole resonance. Fine. Now, after doing so much mathematics, you must be wondering, okay, so what was our goal basically? Well, our goal was to really see that the levels predicted by harmonic oscillator, whether they do match, how much do they match MAT, with experiments. And unfortunately, if we do all these estimates, all those calculations, then we see that we can explain the closed shells for the levels 2, 8, 20 in experiment with the experimental data, but not above. So we can explain only up to 2, 8, 20 and so on and so forth. So this means that basically we can observe that the closed shells appear in levels 2, 8, 20 in agreement with the experimental facts, since the nuclei should close these levels with magic number. But the same, it does not happen in closed shells larger than 20, which is in disagreement. So we can say that this model is no good. Okay, so you see, this is our first choice, as you are. So what do we do next? Next, we do another choice. We choose infinite square well. Infinite square well potential. Next choice, as you are. Okay, now you see, even if we do so, then the same thing again happens. There also, we don't get, after all those computations, you will see that the nucleon numbers, magic numbers, we cannot explain for more than 20. So after that, what do? Let's do some other choice. Now you see, the nuclear potential should actually have an intermediary form between the harmonic oscillator and the square well, in between form. So this is like this and this is just like this. So it should be something in between. And what is that? This in between is basically your Woods section potential. So this is our third choice of UR. So Woods section potential. And what is the form? The form is basically like this: VR is equal to V0 divided by 1 plus exponential small r minus capital R divided by A. Right, here you see this small r, capital R and A are just parameters. Now for this you have to do a numerical solution. But again, even after doing all this stuff, the moral of the story is, no matter what you choose, whether it is harmonic oscillator, whether it is infinite square well, or whether it is section Woods or Wood section potential, we can never explain the magic numbers, not magic numbers, but I want to say the closed shells, right? In a way, it is a representation of the magic numbers above shells above, say, 20. We can never do so. So what do? Well, in 1949, a major improvement, 1949, So because of this, people lost interest in this shell model. But later on in this time, what happened was that Maria Mayer and Haxel Jensen and Swiss independently, they introduced a term of spin-orbit interaction. So they introduced a spin-orbit interaction similar to that of we find in atomic physics, and the nature is like this, where Fr is a radial function that should be obtained by comparing with experiments from experiments, right? Okay, so let's see what we can do now. Now you see a spin orbit term actually appears. Okay, so yes, as I was saying, yeah, a spin orbit term already appears in atomic physics. And what is the reason? The reason is because of interaction between the magnetic moment of electrons. So we have atomic physics spin orbit interaction, and this is because of interaction between magnetic moments of electron and magnetic field created by orbital motion, right? Now in nuclear physics, this term however has a different nature and is related to the quantum field properties of an assembly of nucleons. Now we will see that the addition of such a term to the potential alters the energy values. Of course, it should alter. Now what about the new values? The new values, let us write them, the new values to the first order, the new values we can write like this: psi star h psi, and so this is just n plus 3 by 2 h cross omega plus alpha psi star fr L dot s into psi, where of course alpha is a proportionality constant. Now if we suppose that the spin orbit term is small and that it can be treated as a small perturbation, then the wave functions here are basically those of a central potential. So what do we do next? Let us expand. You must remember that we can write like this. So j square minus L square minus S square all divided by 2. So as a result of this, we can write for j is equal to L plus half, and also this is equal to minus of half L plus 1 for j is equal to L minus half. So you see what happens is that the spin orbit interaction, it basically, so spin orbit interaction basically removes the degeneracy in J and anticipating that the best experimental result will be obtained if the orbitals for larger J have the energy lowered, we admit a negative value of alpha. As a result, we can write the energy increment like this. J is equal to L plus half is equal to minus mod of alpha average value of FR into L by 2. Similarly, we can write for other value J is equal to L minus half. This is equal to plus alpha modulus into average value of FR into half half of L plus 1. Fine. And you see, after doing this, what is the result? The end result is the following. So you see, this is the end result. So what you can see here is basically the level scheme of the shell model showing the break of the degeneracy here in J caused by the spin orbit term and the emergence of the magic numbers. Up to this point it is okay. So what about higher values? Here you see, so 2, 8, 20, they were being reproduced previously, but now after we can match this A and FR, then we can match them with experiments so that you see we can get back our magic numbers. So this is the emergence of the magic numbers in the shell closing, and this is all due to this L dot S interactions introduction. Okay, now the values in this first set of parentheses include the number of nucleons of each type. This is the total number, and this is the number of nucleons of each type. So this is just for proton. Similarly for neutron we will have. So basically number of nucleons of each type that the level admits, and the values in the second one is basically the total number of the nucleons again of each type. So we have these shells independently for protons and for neutrons. Okay. You see, the ordering of the levels is not rigid, and in fact there could be level inversions when changes occur in the form of the potential, and that can happen if we go away from the stability as well, when the potential changes, right? Okay, so now we will use this level scheme to establish the single particle model or extreme shell model. Okay, so let us talk about that. So single particle model or extreme shell model. Now in this version, the model allows that an odd nucleon is composed of so basically in this model an odd nucleus, not nucleon, is basically composed of inert even core plus unpaired nucleon. Okay, and that this last nucleon basically determines properties. Okay, now let's do an example. Let's take 17 oxygen as an example. So let us take as an example 17 oxygen, right? So you see the nucleus has basically how many protons? 8 protons, And how many neutrons? 9 neutrons. So basically we can think of it as 16 oxygen, 8 plus 1 extra neutron. Now where will that 16, what will, let me write this. So 16 oxygen means, in this case, this is all filled up for each proton and neutron. So let me write it separately. আমি সেপারেটলি এইখানে বানাতে পারি, মানে সাফ করে। Now this is for protons, and similarly here we can have the same thing for neutrons, pi and nu. Now 8 and 8. So here 2, 1, 2, 3, 4, and here 5, 6. They are all filled up. Total 8. What about this? 1, 2, 3, 4. Again 1, 2. I am using different notation. You have also noticed. Here circles, here cross. But here we have an extra neutron. And where does it go? 1d5 half. It is going. Right? So basically, this neutron configuration, this whole thing, we can also write in words like this. 1s half, 2 nu, 1p 3 by 2, 4 nu, next again 1p half, 2 nu, right, 1s half, 2 nu, 1p 3 by 2, 4 nu, again 1p half, 2 nu, next 1d 5 half, just nu. Okay, so this is just the neutron configuration, and so the configuration of the neutrons in 17 oxygen, the one unpaired one is this one. And where is this? In d5 half. So the ground state spin of 17 oxygen will be 5 by 2. And what is the parity? L. D is equal to how much? Parity is positive. Why? Because this is L is equal to 2. Okay, so we have the ground state spin parity is J pi is equal to 5 by 2 plus. And this is in agreement with experiment. So here you see this extreme shell model works very well. But remember, this works very well only when we have a nucleon above a closed core, as in the example. It can also work very well for, say, here your 15 oxygen. What will happen for 15 oxygen? For 15 oxygen, basically, we will have one hole or absence of a neutron in the closed shell. Right? And you can also check that for 15 oxygen, you can correctly explain that the ground state spin is just half minus here. However, you see, there are situations where the model needs a certain adaptation. Say, for example, for the stable nuclei, say 203 thallium and say 205 thallium, they have how much? 81 protons and a resulting hole in 11 by 2. And the ground state spin is, however, the ground state spin is basically half plus instead of 11 by 2 minus. Now, in order to understand what happens, it is necessary to recall that the model in the simple form that we are using, it totally neglects the individual interactions of the nucleons. Come on, you remember we talked about this term minus ui something. So we are just assuming that this term is equal to 0. How can you make 0 a two body effect using just a one body effect? It can never happen. Of course, we can have situations where it will be small, but it can never go 0. Right? So basically, we can never neglect. If we do neglect these individual interactions or residual interactions, then this is what will happen. We will get wrong predictions. So a correction of the model is required to take into account certain nucleon interactions that we know are present and that are part of the residual interaction. Okay. Now let us talk about such class of interactions that needs to be taken into account. Okay, now one of the very important class is your pairing force. Let me talk about it first. Again, I am not going to do any mathematics, just going to talk about the basics regarding this. Now, what happens here is that it basically involves a proton or a neutron pair of equal orbits. So basically we have a proton or neutron pair of equal orbits n, L, J with symmetric values of mj. Now, a collision of these particles can take the pair to other orbits with the same quantum numbers n, L, J, but with a new projection. Collision. Same n, L, J, but new projection. And what is it? Say mj prime, comma, minus mj prime. Now these collisions, they conserve energy. You see the 2j1 plus states are degenerate. So they conserve energy, angular momentum and parity, and we expect that there is a permanent alteration between the several possible values of the pair mj, minus mj. Now the interaction between these two nucleons, these two nucleons with projections mj and minus of mj, okay, in these circumstances is known as this pairing force. It leads to an increase of the binding energy of the nucleus. So what is happening is that they are moving in the same orbit but in opposite directions. So one is moving like this, another is like this. So what is happening at each time, there is very large overlap between them. So this is the reason for increase in the binding energy. Since you see the nucleons belong to the same orbit, their wave functions have the same space distribution and the average proximity between them is maximum. So this is what I am saying. Maximum. One is moving like this, another is moving like this. So in one orbit, there will be two times they can come close to each other. I'm just giving a classical idea regarding this. Now you see, as the nuclear force is attractive, this leads to an increase in the binding energy, as I was saying. Now the pairing force is responsible for the pairing term of the mass formula. Remember, you learnt in the graduation. Now it is the same type of force that acting between the conduction electrons of a metal in spatial circumstances and at low temperature, what does it yield? It yields the superconductivity phenomena. Okay. Now you see, what about the J dependence of the pairing interaction? Well, you see, this pairing force, this increases with value of J. Why? Since the larger the angular momentum J, the larger the location of the wave function of the nucleon around the classical orbit, and also the stronger the argument of the previous discussion. Now what does this mean is that it is sometimes more energetically advantageous that the isolated nucleon is not in the last level but below it, leaving the last level of a group of unpaired nucleons. Now this happens in our example of thallium. The hole is located, so what happens in thallium is that the hole is located not in H11 by 2 but in S half, leaving the orbital H11 by 2 of high J occupied by pair of protons. Another example is 207 lead, where hole in the closed shell of 126 neutrons is not in I13 by 2 but in P half, and this results in the value of half minus for the spin of its ground state. Let us consider a different type of example, say 23 sodium. Now this nucleus has the three last protons in orbital 1d 5 half. Sodium means 11 and this is 12, right? So three last protons in the orbital 1d 5 half. Now the value of the spin J is however 3 by 2. How can you get 3 by 2? What is the reason? কি করে হতে পারে? Now this is basically an example of a flaw in the predictions of the extreme shell model. So we have a flaw in predictions of extreme shell model. Actually here you see, it is the coupling between the three nucleons that determines the value of the spin, and not separately the value of J of each of them. So these three protons, they are doing something. Okay. And just by neglecting the residual interaction, we are actually not seeing the entire something that these three protons are doing. So we have to look into this picture, and for that we have to consider the residual interaction. Okay. Any questions? Okay. Let me show you yet another example. Say, so you are roughly getting the idea that slowly life is becoming troublesome for us because of our simple negligence of the fact that we are just not considering the residual interaction. Now let us look into a different example. Say the level scheme of 41 calcium. 41 calcium. So this is the level scheme. I'm just showing this to you. This is the spin parity. These are the energies. 1.943, and here these are the energies in MeV. 2.010, 3 by 2 plus and 3 by 2 minus. So till now we have talked about the ground state spins. So right now I was just talking to you about this fact that we have got this 1d 5/2 level. Now suppose if we have an unpaired nucleon over here and all the other filled up below, then the spin of the nucleus will be described just by this unpaired nucleon, that is 5/2. But instead of 1, if we have 2 more, then the spin will not be again 5/2 because these two are doing a sort of pairing interaction, so they will be left out. But no, this is not happening. Instead, along with that, of course pairing is there, but something more is that. What is that? Is that the 3 are working together. There is a residual interaction involved, and as a result of this spin of this nucleon is not at all equal to 5/2. This is what I have been saying. Now let us use this argument to discuss this 41 calcium. Now you see, for the case of 41 calcium, the ground state is 7/2 minus. Since the extra neutron, the ground state is 7 by minus, since you see I am writing it over here, since extra neutron occupies orbital F7/2. 41 calcium means here it is 21. So if you look into this picture, 40 calcium here. So 1d 3/2, everyone is filled here, and 1 unpaired in 1f7/2 over here. Right, 1f7/2. So the ground state is 7/2 minus. Now what about the first excited state level? It basically corresponds to the jump of the neutron in 1p 3/2. It means, so this neutron in 1f7/2, if it does the jump or it goes an excitation to this level, then what will be the spin of the first excited state? It will be 3/2. But we have got P, that means L is equal to 1. So parity will be negative, and so you see the spin is 3/2 minus. Right. Now the second excited state, 3/2 plus, is obtained by the passage of neutron from 1d 3/2 to 1f7/2, leaving a hole in the 1d 3/2. Let me again show you. So again here, this is what I am saying, is that the second excited state, 3/2 plus, is obtained by the passage of a neutron from this 1d 3/2 over here to 1f7/2, and this leaves a hole in 1d 3/2. So what happens is that the first case is when this so 1f7/2 to 1d 3/2, this happens, right? You see this diagram over here, sorry, 1d 3/2 is over here, this is 1f7/2, right? Just a second, let me write it down. So we have got 1d 3/2, 1f7/2, and then this is p 3 half. Fine. Now the unpaired neutron is over here. Okay, so the ground state is just 7 by 2 minus. Next, first excited state, it goes over here. Right. What about the second excited state? The second excited state energetically happens when this pair is broken over here. One goes here and it forms J is equal to 0, but the hole is left as a result. And this causes this 3 by 2 plus. So this is what I mean. Okay, the second excited state is obtained by the passage of neutron from 1d 3 half to 1f 7 half, leaving a hole in 1d 3 half. So you see, it must be noted also that in very few cases the single particle model gets to a reasonable predictions of spins and energies of the excited state. Now in our next class I will talk about this scenario, 2 or more nucleons in the state, and how we deal with this residual interaction. Okay, questions?